There is a moon out at Saturn that you could lay across the state of Arizona and still have room to spare. It is a frozen white pebble, barely 300 miles wide, circling a giant ringed planet nearly 1 billion miles from the Sun. For most of the time we have known about it, we treated it as exactly that, a pebble, a rounding error, one more icy speck in a system that has more than 140 of them. And then, in 2023, we pointed the most powerful telescope ever built at it. And what came back through that golden mirror was something nobody was prepared for. A jet of water, erupting off the south pole of this tiny moon and rising more than 6,000 miles into space. That is farther than the distance straight across the continental United States, twice over, fired out of a world small enough to fit inside a single American state. This is the story of what the most sensitive telescope in history found out there in the dark, around a moon almost nobody thinks about, and why a frozen speck named Enceladus has quietly become one of the most important places in the entire solar system. To understand why that fountain matters, you have to understand what Enceladus was supposed to be. It was discovered in 1789 by William Herschel, the same astronomer who had found the planet Uranus a few years earlier. Through the telescopes of his era, it was nothing but a faint dot of light, lost in the glare of Saturn's rings. For nearly 200 years after that, it stayed a dot. It sits in the shadow of its famous neighbour, Titan. Titan is enormous, bigger than the planet Mercury, wrapped in a thick orange atmosphere and dotted with lakes of liquid methane. Titan is the moon that got the attention. Enceladus was just the small bright one nearby, white and quiet and apparently dead. A snowball orbiting in the cold. Then we sent something to go and look. In 2004, after a 7-year journey, a spacecraft called Cassini slipped into orbit around Saturn. It was the size of a small bus, and it spent the next 13 years circling the planet and its moons, sending photographs and measurements back across the solar system. And almost immediately, Enceladus stopped behaving like a snowball. In 2005, Cassini swung past the little moon and noticed something strange near its south pole. The instruments detected a faint haze, a plume of fine particles hanging above the surface where there should have been nothing at all. The cameras turned, the spacecraft looked closer, and there it was. Geysers, towering jets of water ice and vapour, spraying continuously out of the bottom of the moon and into the black. A dead world does not do this. A frozen pebble does not have fountains. When Cassini mapped the source of those jets, it found a set of long, parallel cracks slashed across the South Pole. 4 enormous fractures, running roughly side by side, each one over 80 miles long. Scientists nicknamed them the tiger stripes, because that is exactly what they look like from orbit. dark claw marks raked across a sheet of white ice. The tiger stripes are warm. Not warm the way Earth is warm, but warmer than the deep frozen ice around them, glowing in infrared like the embers of something buried. And out of those warm cracks, water is venting into space at over 800 miles an hour. The little moon is losing hundreds of pounds of water every second, spraying its own substance away into the dark. Some of it falls back as snow. Some of it never comes back at all. That water doesn't just disappear. It drifts out and joins one of Saturn's rings. The faint, wide outer band, called the E-ring, is not made of debris left over from the planet's formation, the way most rings are. It is made almost entirely of fresh ice grains sprayed out of Enceladus. This one tiny moon is exhaling so much water that it is building and feeding an entire ring around its planet. We had been looking at the evidence for decades without realizing what it meant. The ring was the moon's breath, made visible. For years, the close-up data from Cassini was all we had. The spacecraft sampled the plume directly, flying straight through the jets at thousands of miles an hour and catching the ice grains on its instruments. It tasted them as they hit. And then, in September of 2017, Cassini ran low on fuel. To make sure it could never crash into Enceladus and contaminate that pristine ice, mission controllers deliberately steered it down into Saturn itself, where it burned up in the atmosphere. Our one set of eyes at Saturn was gone. The plume kept erupting out there in the dark, and we had no way to look at it. Until James Webb. The James Webb Space Telescope does not work the way Cassini did. It never has to leave its position 1,000,000 miles from Earth. It does not take photographs in the way you might imagine either. It reads light. Every wavelength that a distant object reflects or emits is a chemical fingerprint, and Webb is built to read those fingerprints with a precision no telescope in history has ever had. It does not have to fly to Enceladus. It just has to stare at the right pinprick of light and let the photons do the work. In 2023, an international team led by a scientist named Geronimo Villanueva did exactly that. They turned Webb toward Enceladus and waited. And what the telescope measured stopped people in their tracks. The plume was not a few hundred miles tall, the way it appears in the Cassini photographs. Webb saw it stretching more than 6,000 miles out from the moon. That is roughly 40 times the width of Enceladus itself. Imagine a fountain erupting from a garden sprinkler, except the spray reaches 40 times wider than the entire lawn. A moon 300 miles across is launching a column of water more than 6,000 miles into space. And it is brutally cold out there. The water vapor in that plume sits at a temperature low enough that it should freeze almost instantly. And yet the jet holds together across that enormous distance, feeding a vast halo of vapor that wraps all the way around Saturn. Nothing else in the solar system does this. There is no other world we know of that is bleeding its insides into space on this scale, in plain view, waiting for us to read it. But the size of the fountain is not the real story. The real story is where the water is coming from. Because all of that ice is not melting off the surface. It is being pushed up from somewhere far below. Underneath the frozen shell of Enceladus, there is an ocean. Not a pocket, not a frozen slush. A global ocean of liquid salt water, wrapped completely around the moon, hidden beneath 15 or 20 miles of solid ice. We did not guess this, we measured it. As Enceladus orbits Saturn, it wobbles very slightly on its axis, rocking back and forth as it goes. Scientists tracked that wobble over years of Cassini data, and it was too large. The moon was rocking more than it should if it were frozen solid all the way through. The only way to explain the motion was if the icy crust were floating, sliding on a layer of liquid underneath. The wobble was the ocean, sloshing. That ocean is real, and it is enormous. Despite the moon being so small, the water beneath the ice may be deeper than the oceans on Earth. Which raises the obvious question: how is there liquid water at all, 1 billion miles from the sun, where everything should be frozen as hard as rock? The answer is Saturn itself. As Enceladus circles the giant planet, Saturn's immense gravity pulls on it unevenly, squeezing and stretching the little moon as it goes around. That constant flexing works the interior like a person bending a paperclip back and forth until it grows warm. The friction generates heat deep inside, and that heat is what keeps the ocean from freezing. Enceladus is not warmed by the sun. It is warmed by the relentless pull of the planet it orbits. The tides are the furnace. That same pull does something you can actually watch. Enceladus does not circle Saturn in a perfect ring. It swings a little closer and then a little farther on each orbit. When it pulls away, Saturn's grip stretches the moon hardest. The tiger stripes flex open and the geysers roar. When it swings back in, the cracks ease shut and the jets fade. The plume breathes in time with the orbit, growing and shrinking every few days. How long this has been going on, nobody is sure. Some models suggest the ocean is ancient, billions of years old, steady enough for chemistry to do slow and patient work. Others argue it may be far younger. For the question of life, that difference matters enormously, because life, as far as we know, needs time. And at the very bottom, that ocean is pressed against a core of warm rock. That detail is where Enceladus goes from strange to extraordinary. Because when ocean water sits against hot rock, things happen. On the floor of our own oceans, in places where heated water rises up through cracks in the seabed, we find hydrothermal vents. And around those vents, in total darkness, miles below the surface, we find life. Whole crowded gardens of it. Tube worms taller than a person, ghost white crabs, mats of bacteria, entire ecosystems that have never seen a single ray of sunlight. They do not run on the sun, they run on the chemistry of warm water meeting rock. Some scientists believe that vents exactly like these are where life on Earth first began. Cassini found the fingerprints of that same process at Enceladus. In the plume, it detected tiny grains of silica, a mineral that only forms when water is heated to high temperatures against rock and then cooled quickly. The presence of those grains is one of the strongest signs we have that the floor of the Enceladus ocean has hot springs, just like the bottom of the sea on Earth. A moon nearly 1 billion miles from the sun has warm water and rock meeting in the dark, the same recipe that feeds life at the bottom of our own world. Then Cassini found something even more pointed. In the gas escaping from the plume, it measured molecular hydrogen. On Earth, hydrogen welling up from hydrothermal vents is food. Certain microbes breathe it, combining it with carbon dioxide to make methane and drawing energy from the reaction. The hydrogen at Enceladus means there is a chemical energy source in that ocean, a battery that life as we understand it could plug into. And alongside it, scientists later identified hydrogen cyanide, a molecule that sounds like poison but is one of the most useful starting materials in all of chemistry. A building block from which the components of living cells can be assembled. And then there is the methane. Cassini measured a surprising amount of it in the plume, more than scientists expected to find. On Earth, a great deal of the methane in places like the deep sea is produced by living things, by microbes exhaling it as waste. So one team built a careful model to ask a simple question. Could ordinary chemistry alone account for all the methane at Enceladus? Or would you need something more? The answer they reached was unsettling. The numbers were difficult to explain without invoking biology, without imagining tiny methane-producing microbes living around the vents on the ocean floor. That is not proof. Hot rock and water can also make methane, with no life involved at all, and the scientists themselves were careful to say so. But it is a result that refuses to go away, and nobody has been able to rule it out. Water, warmth, energy. The list of things you need for life kept getting checked off, one by one, from a moon we had written off as a frozen rock. And then came the ingredient that completed the set. Life on Earth is built from 6 essential elements: carbon, hydrogen, nitrogen, oxygen, sulfur, and phosphorus. By the early 2020s, scientists had found traces of nearly all of them at Enceladus. But phosphorus, the rarest and the hardest to detect, was missing. Without it, you do not get DNA. You do not get the molecules that store energy inside a living cell. Phosphorus is not optional. In 2023, a team re-examining the old Cassini measurements of the ice grains in Saturn's E-ring found it. Sodium phosphates, dissolved in the water that had sprayed off Enceladus. It was the first time phosphorus had ever been detected in an ocean beyond Earth, and the concentrations were startlingly high, hundreds of times richer than the water in our own seas. That was the moment the picture clicked into place. Every single ingredient that life on Earth requires, all 6 elements, plus liquid water, plus warmth, plus a source of energy, all of it present, all at once, in one small ocean at the edge of the solar system. There is no other place we have ever found where the entire checklist is complete. Not Mars, not anywhere. Just this frozen speck spraying the recipe for life out into space, where our instruments can catch it as it goes by. And the discoveries are not finished. As recently as 2025, scientists went back to a single set of measurements Cassini took in 2008, when the spacecraft flew through the plume just 13 miles above the surface and slammed into the ice grains at high speed. Those grains were fresh, only minutes old, having just been flung up from the ocean below. And buried in that old data, researchers found new, complex organic molecules that had never been identified before. Larger, more intricate carbon compounds, the kind of chemistry that, on Earth, sits along the road that leads toward biology. These were not ancient particles weathered by space. They were fresh from the ocean, carrying its chemistry directly to the instrument. At this point, it would be easy to get carried away, so it is worth stopping and being honest about what we do not know. Because not every scientist reads this story the same way, and the people who push back are not cranks. They are doing exactly what good science demands. In 2025, another team ran a careful set of laboratory experiments. They took ice, like the ice on Enceladus, and bombarded it with radiation, the same kind of radiation that constantly bathes the Moon's surface from Saturn's powerful magnetic field. And they found that some of those complex organic molecules, the very ones we have been getting excited about, can be manufactured by radiation alone, cooked up on the frozen surface with no ocean involved at all. It is a genuinely deflating possibility, and it has to be taken seriously. If the radiation on the surface can produce the same chemistry, then some of the molecules in the plume might not be messages from a living ocean. They might just be the byproduct of particles hitting ice. The plumes, in that case, could be fooling us. The counter-argument is the fresh grains. The molecules Cassini caught 13 miles up were minutes old, straight from the vents, with no time to sit on the surface and bake in radiation. That points back toward the ocean as the source. But the truth is, we cannot yet be certain. Both things might be happening at once. The honest answer, the one the scientists themselves give, is that we do not know. Not for sure, not yet. And that uncertainty is the whole reason this matters so much. We are standing at the edge of one of the biggest questions a person can ask. Are we alone? And the evidence is sitting in an ocean we have already tasted, but cannot quite read. Think about that for a moment. A spacecraft from Earth flew through the spray of an alien sea and caught its chemistry on the way past. We have, in the most literal sense, already sampled the water of another world. We just cannot yet tell what the sample is trying to say. Let yourself stand on that ice. If you could somehow set foot on the south pole of Enceladus, near the tiger stripes, this is what you would find. A landscape of blue-white ice, cracked and broken, stretching out under a black sky. The sun would be there, but it would be tiny and far, giving off about 1% of the warmth it gives the Earth. There would be almost no heat from it at all, and rising up around you, silent and constant, would be the geysers. Vast curtains of ice crystals fountaining out of the cracks in the ground, climbing into the dark, catching what little sunlight there is and glittering as they rise. Some of the spray would fall back as a fine, slow snow, drifting down onto your shoulders. The rest would keep climbing, up past where you could follow it, out toward the rings. And hanging over all of it, filling a huge part of the sky, would be Saturn itself. The giant planet and its rings, looming silently above a frozen world that is quietly, endlessly, breathing its ocean out into space. You would be standing on the thin shell of ice that is the only thing separating you from a sea that may be the most promising place to find life in the entire solar system. And here is the part that is hard to sit with. We have all of this. We know the ocean is there. We know it has warmth, energy, and every ingredient on the list. We have even tasted its chemistry as it sprayed past our spacecraft. And right now, there is no funded mission on the books to go back. Scientists have designed one, a concept for an orbiter that would circle Enceladus, fly through the plume again and again with modern instruments, and finally answer the question of whether anything is alive down there. It is widely considered one of the most important missions we could possibly fly, but it has not been built. It has not been paid for. The journey takes the better part of a decade. The engineering is hard, and the budget for the outer solar system has been stretched thin for years. If we did go back, we now know what to look for. A modern spacecraft flying through the plume could weigh the individual molecules in the spray, searching not just for the ingredients of life, but for its signatures, the lopsided patterns and repeating structures that living chemistry leaves behind and dead chemistry does not. It could, in principle, catch a cell. We would not have to land or drill or melt through miles of ice. We would only have to fly through the fountains slowly enough with the right instruments and read what the ocean has been throwing at us all along. So for now, Webb is the best tool we have. Every so often, when Enceladus swings into the part of the sky the telescope can safely observe, Webb turns and stares at it again, refining the chemistry, tightening the picture, adding one more data point to the question of what is really happening out there. And every look so far has made the little moon stranger and more alive than it was before. Step back far enough and Enceladus stops looking like an exception. It starts looking like a warning, or maybe an invitation, because it is not the only ocean out there. Jupiter's moon Europa hides a sea beneath its ice that may hold more water than all of Earth's oceans combined. Titan, the giant neighbour next door, has a buried ocean of its own beneath its methane lakes. Even Pluto, far out in the cold, may be hiding liquid water deep below its frozen shell. For most of the last century, we thought of the outer solar system as a dead place. Gas, ice and rock, too cold and too far away to matter. We were wrong. The outer solar system is full of hidden oceans. Dark, salty seas, sealed under miles of ice, kept warm by the slow heat of the worlds that hold them. Each one a sealed experiment that has been running quietly for billions of years with no one watching. Enceladus is simply the one that decided to show us. the one that cracked open at the South Pole and started spraying its secret into space, where a telescope 1,000,000 miles from Earth could finally read it. That is what makes this small moon so important. It is the one ocean world that brings its ocean to us. We do not have to drill through the ice. We do not even have to land. We just have to catch what it is already throwing into the sky. A species on a small rocky planet using a mirror parked 1,000,000 miles out in the cold to watch a fountain of seawater erupt off a frozen moon it has no way to reach. Reading the chemistry of an alien ocean in the light of a jet 6,000 miles tall. We may be looking at the ingredients of life sprayed out into the dark by a world we once dismissed as a pebble. We do not yet know what is down there. We may not know for a very long time. But Enceladus has made one thing clear. The cold and the distance out there are real. But so is the water. And so is everything that water carries. There is far more happening in the dark than we ever imagined, and we have barely started to look.